All right, ladies and gentlemen, let's see if we have some audio here. Okay, the audio is going on. Let me double check something here. Sometimes I forget to send this to the right class. Is today the 11th? I think it is. I think we did do that. I think we did do the announcement. Did we do the announcement? Yeah, I think we did. Okay. So everything seems to be up in order or up working. Anyway. Okay. So here's what I want to do for you guys. Come on. I guess you guys are here in Math 227. So there was some things that I wanted to get back to, if you guys remember. We talked about probability distributions. You guys remember that? But this is under the worksheet of probability distributions and expected value. So I'm going to put the link here. Okay, let's put that link. So we didn't talk about the expected value. Do you guys remember this? So it is in the notes. However, let me do the following here. It's in our notes. So I'm going to go to Excel here. And this is going to talk a little bit about what we're talking about. Okay. Now, remember, we did a study here for the number of children people have. Now, this is kind of going back to that whole idea. Number of children, if you guys remember. Right? So in Microsoft Excel, X, the random variable, is the number of children. These are all the responses, right? Some people said, 0? Some people said 1, 2, 3, 4, and in this example, 5. And we got the frequency values. We computed the relative frequencies. This is the stuff we did in day 1, if you guys remember. And there's something bothering me here. I'm going to do this again. Okay. And that's odd to me. But anyway, okay. Did anybody see why that's odd? Well, there's something really strange. Let's do this again. We're going to sum these values here. All right, whatever. It should not be 1, but okay, whatever. Well, I mean, it should be 1. It should be close to 1. Here's what I'm saying. What I did was I took the relative frequency table here for the number of children, the stuff we did first week. You guys know how to do this. You had it on a test. Blessed you. And then what do we do over here? What's this called over here? This is a probability distribution. Is that right? So I'm going to take a step back and go over this probability distribution table. And remember, X is different values. It's how many children people have. I put the words here. No children, 1 child, 2 child, 3 children, 4 children, 5 children. This is your random variable X. And then these are the relative frequency values, which are really your probability values. So a relative frequency table is really a probability distribution. And that's what we've been working with, the notation and language. And this is what I'm saying. This is what bothers me. I got the same answers here, but when I sum them, it's 0.999. Over here, it's 1. So it's like a weird thing in Microsoft Excel. I don't know. That's why I was freaked out about it. What's going on? And of course, this is a percent language, so it should be 99%. So the point I'm making is, if you guys looked over some of that homework, probability distributions, when you sum them, it should be close to 1 or equal to 1. It all depends on if you approximate. So that's how you know you have a probability distribution, a probability table of probability values. The sum needs to be what? 1, okay? But the question I want to ask you guys today is the following, okay? For any distribution, let's go to the iPad now. We can ask these questions here for any probability distribution. What is the mean of the probability distribution? It has a mean. Like, what's the average number of children people have in the table? Because remember, the mean is an extremely important measure, right? The mean is your summary. It's like the center. It's the average. So we always care about that mean, ladies and gentlemen. It's one big measure. It's a very big measure, the mean. And that mean is, in fact, represented by this letter mu. Okay? Now, in case you guys didn't know, mu is a Greek letter. And somewhere on my desktop, darn it, let me look for it. All these things I have to move out of the way. Oh my God, what is this? Where's my mu? Mu. There should be a way to go to my desktop. There we go. I got mu and I got sigma. So put this way over here. No, where's mu? Mu is hiding. Where are you, mu? Oh, whatever. Whatever. All right. Let's get back to what we're doing. No, we don't want that. Come on. Where are you? We're going to go to the iPad. It's supposed to be on the iPad. There we are. Anyway. Okay, I guess we're right here. So mu. I guess I'm going to have to find it one other day. Let me give you the definition here, okay? Mu, this here, this definition, this is the mean. This is also called the expected value. It's also known as the long run average. We're going to have a discussion on this today. This is what really makes the world go round. Expectation. It has various names. Sum, where all outcomes x, p of x. Okay? So this is the name of all of this. You're going to get the what? The mean, expected value, long run average, expectation. So with any distribution, you have the random variable x, its probability values. So we're going to have to find that column. We're going to have to find the x, p of x column. It's very simple to do. And then what does this mean here? Do you guys remember? What is this? That's to sum. So you're going to add. Okay, we're going to add. You say, what am I going to add? I'm going to add all of these values. That's what it means. Add the x p of x values. And then you say, what does it mean for all x? Well, you're going to do this product for every x value. So if I go back over here in Microsoft Excel, here's what I want to share with you guys. Okay. We're really talking about, again, these two values here. We're going to have to create a column. The column is going to be x, p of x. And so you say, how do I get that? Well, let's go back to Microsoft Excel. Here's what I mean. We say, okay, here's this x p of x column right in here. And I'm going to color this thing orange here so you guys can see that. Maybe is that too dark? Anyway. So I'm going to say equal. This is x times p of x. So I'm going to have to multiply that there. And I'm going to have to get some numbers that are bigger than that. I have to center those numbers. And what size? I think 20. Okay. And I'm going to do that for every x value. So I'm going to do what's called autofill. This does it automatically for me. So that's what they're talking about when I say to you, and I have my, go back to iPad. You're looking for all of this right here in orange. That's the xp of x column. So that's what you need to do. Now you need to add them. Is that true? And if I add them, you say, well, what happens when I add them? Well, let's add them now. Take that sum. This is a summation. I want to add these numbers here is what I'm doing. And when I get that, what's this answer here? Do you guys see this here? What is that? 1.866. So what I just found here is the mean of the distribution, the average of the distribution. Now, what does the distribution represent? Remember this x value? What does it represent? Number of children. So the number of 1.866 means that's the average number of children that's in this table. So if I select a person at random, I can say, you know what? I can expect they're going to have about 1.866 children. Okay, this is gathering data on children, but you're looking at it as a probability distribution. And so now, ladies and gentlemen, what that even means now is this. Mu, the Greek letter mu, this is the number of children. You ever hear the phrase, and maybe it used to be said, 1.866 children. It used to be said that couples in America have 2.2 children. This is an important measure. Demographics, you guys know? It's important to know how many children people are having. So by this table and by this data, this information, couples are having 1.866 children. Okay, you guys okay with that? You can find the mean, the average. Why do you guys think having children is so important? Why is having children important for a society? Are children even important? Do we even need to know why to find the average number of children? Why isn't any society having children important? Huh? Yeah. Yeah, I mean, I hate to say it this way to you guys. It's kind of a little bit, somewhat common sense, right? Who's supposed to take care of you as you go old? Children? The next generation? Prior generations? So what happens in societies where you don't have growth in children is that society ages and there isn't enough people to support the older people. It's a serious problem. Like Social Security, for example. You go, what is Social Security? Well, what you guys don't realize is it's based on having a number of people support the people who have retired. They have to have an income. So it might take 5 people to support one person in retirement age. So 5 working age people. What happens if that pool of working age people starts to decline? Then what starts to happen is there's going to be some issues. So if that really declines that population, you don't have actually people who can support older people. And there are societies that are aging that are you can read about and you can hear in the news and you can study and talk about that. Societies that are aging, they don't have enough people to support the older population. That's a serious problem. That represents a lot of serious implications in their future. Okay? Especially if you say, what's going on? You go, well, Mr. Judge, you're going to turn this into politics. Well, you know what's good is you have academic freedom because we're talking about numbers here, right? Like, for example, one of the problems that Russia's having right now with their war in Ukraine, a serious problem, is what's going to happen to them. A lot of people are dying in Russia. And a lot are leaving. Okay. So you say, well, okay, well, what does that mean? It means they're going to really have a serious problem in the future because of that loss of life and the loss of people who are leaving that country. And yes, there is a brain drain. That's true. That's very true. But a society can't afford to lose people like that. If it does, there's a lot of dark implications about their future. You guys know what I mean? It's not even a political thing. It's more of a practical thing. So you say, is it practically a good idea to do what they're doing to their own society? I don't know what they plan on doing in the future, but maybe conquest and capturing and enslaving people is the idea because they're going to need a population to support their what? Current population. And if you don't have that population, if you don't have kids, if you don't have a society that can read, write, and do arithmetic and to progress, you got a real serious problem. One of the reasons America is what it is because we don't rely solely on our what? On our population growth internally. We have immigration. That's one of the strengths of it because now it's not as simple for us as is other people or other societies. In other words, that new influx of immigrants really helps sustain the nation, in a lot of ways. So, just kind of throw out to you, you might say, boy, Mr. Judge, you're making us compute the number of children. Why do I even care, about a probability distribution on children? Because that's an important measure. Finding the mean of a distribution, the average, the summary. And in this case, it's just something simple like children. How many? Okay, you guys know what I'm saying? There's a lot of real applications of what we're doing. So this is the average number of children. So, I want you guys to kind of look at that. And you could do this for any distribution. So this is the general, remember, I did probability distribution, but we never did expected value. This is also known as an expected value. But we can compute a mean, and I want you guys to know, we'll get back to it. But I'm going to write it down in our notes. Note, we can compute the variance of a distribution, and that's represented by lowercase sigma to the second power, and the standard deviation of any distribution. And we care about that too, the consistency. So not just the summary, but how consistent that data, right? So these are 2 other measures we're going to get back to by some formulas, but I'm going to focus on this here, all important definition. Yes? Yeah, you know what it is? It's a capital letter mu. It's mu. It's capital mu. And that's a Greek letter. And I was looking for it, and I couldn't find it, so I'm going to have to do that here. I had a little picture of it. Check my what? Yeah. I did, and it's somewhere on my desktop, but I kind of screwed it all up. You know, it's not. I mean, take a look. Even if I do Mu, if I'm going to look here online here, I'm going to share with you guys in the browser here. You go Mu. Yeah, let's look at images for Mu. And this is what I'm looking for. See if I can bring it in. The problem is I don't even have my Ecamm Live video. Where are you? Where are you, video for Ecamm Live? We lost you too? Ah, whatever. Anyway, I'll try to do it this way. It's in the lower right corner. And I go back to the iPad if I can. Okay, and I'm going to bring it in my whatever. That's the Mu. That's what I'm looking for. It's Mu, and I can't even get to where I need to go. Anyway, okay. So Mu. Whatever happened to our screen? Don't know where it is, but okay. Where do I do this here? Yeah. I lost the Ecamm Live screen, but okay, not sure what that is. Whatever. So let's focus on this symbol Mu, ladies and gentlemen. This expected value. Let's focus on this definition, okay? And it's a Greek letter. So remember this. This is Mu. It's not a M. It's actually, ironically, a lowercase m in the Greek alphabet. But it's like a U with a long tooth. Right? Does it look like that? It looks like a U with a long tooth. You guys see that symbol? So anyway, that's the Greek letter Mu. This is what we're going to focus on. This is what makes the world go round. Now I'm going to transition for you guys to show you guys what I'm talking about. Where this definition comes from, there's different ways to use it. One is just simply getting the mean of a distribution or the average of a distribution. Also has another name for this. It's the expectation. Anybody ever go to Vegas? Anybody go to Vegas during this spring break? No? Anybody like going to Vegas? What do you guys do in Vegas? Oh, you play slots. What slot machine do you play? There's a lot of what? I run my own little section that's empty because there's a lot of like people and like a certain section, so I like to stay away from people so I don't get jinxed. Okay, so let me ask you guys this question here, right? What generally happens in Las Vegas when you gamble? Do you guys know what generally happens? What generally happens is that you lose. Is that true? And I know what happens. People say, no, Mr. Judge, when I gamble, I've won. And you might have won. You might say, yes, I have fun. And I gamble and I win at times. It's fun. And people do that, right? But the real purpose, in case you guys didn't know, of any gambling game isn't that you win, is actually that you lose. You might say, what are you talking about? Well, I'm going to simplify this idea, okay? Let's make this very simple. Do you guys know a raffle is pretty much the same kind of thing? So if I say to you, what's the real purpose of a raffle? Do you guys know what a purpose of a raffle really is? Is it to have fun? No. It's not really. Raffles don't exist to have fun. You know why they exist? They exist for what reason? Huh? Let me try to find our window. Where did our window go? Anyway. I don't know. Whatever. Okay. Let me share with you guys this. A raffle, let's say, for example, this. You sell 500 tickets at $3 per ticket. For a chance to win, what are you going to win? PlayStation 5. Okay? So I'm going to share with you guys what's really happening here. Okay? Let's see what happens here. I don't have that. It's weird. So let's see about this here. You know what the purpose of a raffle is? Is to make a profit. So it's not to have fun, ladies and gentlemen. Gonna get rid of that clock. There it is. There it is. There we go. We're back. Find it. I found it. We're dealing with mu. Okay. So profit, ladies and gentlemen, is revenue minus the cost. So here's your real purpose. Profit is revenue minus cost. Do you guys happen to know what revenue is? That's money you bring in. What's the cost? Money you spend to bring in that revenue, okay? It's an extremely important equation in business. So if I said to you guys, what's your revenue here for this model that we're looking at? You sold 500 tickets at $3. What does that mean? What's your revenue? You say, how do you know that's 1,500? Because 3 times 500 is what? 1,500. You guys okay with that? So you brought in revenue. How much did you guys bring in? $1,500. Is that true? But what is the cost? Do you guys know what the cost is? You say, what are you going to win? A PlayStation 5. How much are PS5s? Oh, I don't know. Let's say $600. Okay. So guess what you had to spend for the prize? You had to spend how much money? $600. So what's your profit going to be then? Right? What's your profit? What's 1,500 minus 600? What's 1,500 minus 600? Is that $900? So, ladies and gentlemen, this is the whole point for you guys. The point of a raffle is to do what? Bring money in. It's not to have fun. It's to bring money. Now, this is an extremely important detail. So I'm going to ask you guys this question. We're going to unitize this. What is the profit per ticket sold. You guys know, what do you mean profit per ticket sold? How many tickets did you guys sell? 500. So that means divide by 500. So if I go to the TI calculator here, okay, say, okay, where's that TI? Let's find the TI. If we take the $900 divided by the number of tickets that we sold, that gives you a unitized kind of number. The profit per ticket sold is 1.80. This is dollars, ladies and gentlemen. $900 divided by 500 is going to give you $1.80. This, ladies and gentlemen, is the whole point. Okay, we're looking at what's called the profit per ticket sold. That is the expected value for our raffle. So we can think, and you go, okay, you think about it this way. You go, oh, for every ticket that we sold, how much money did we make? $1.80. You unitize it. Every ticket sold, that's $1.80. $1.80 for every ticket you sold. That's how you think about it. So whenever you have a ticket, you go, but Mr. Judge, a ticket costs $3. I know, but $1.20 went to the what? PlayStation 5. $1.20 went to the cost. What you get per ticket is $1.80. And that's what makes the world go round. You go, oh, great. So every ticket I sell, I get $1.80. And I like that. And that's the deal. That's how this works. So you might say, well, what is this really? Why are you calling it an expected value? Because believe it or not, I'm going to show you guys now, mu, that's not a U, it's not an M, it's a mu, a Greek letter, like a U with a long tooth. I can use this definition to compute this. And that's the transition, to share with you guys how this works in a sort of gambling or model situation where there's two outcomes, win or lose. We can compute an expected value. It's a mean, it's a long run average. They're all the same. So you might say, well, how do I do this from that situation? Okay, how do I use the definition now? Well, for any raffle, like even any gambling game, because that's what a raffle is. Would you guys agree with that? Isn't a raffle a gambling game? What are the two outcomes when you gamble? Good. You can win or you can what? Lose. Is that true? You could win or you can lose. Okay? Now, for this raffle, can you guys tell me what's the probability that you win this raffle? Believe it or not, you can actually figure that part out. What's the probability of winning? It's what? Well, how many tickets did you guys sell? 500. How many tickets are the winning ticket in a raffle for a single prize? One. Does that make sense? There's only one PlayStation. So this is one out of what? Good job. Outstanding. Now, let's see if you're really awake. What's the probability that you lose? 400 and what? 99 out of 500. Isn't that the complement, ladies and gentlemen? Okay, is that easy? All right, good. All right, here you go. All right, now here's the deal. If we're going to get that column of the x times p of x, remember that one in orange like we did earlier to get the average or the mean? Because it's the same thing, it's the same definition. I need to take an x value and multiply it to p of x. However, winning and losing are phrases. They're not numbers. Do you see my point? We need numbers there. So go back over here, and this is how you find the numbers associated with winning and losing, okay? Because this is our x column. This is our probabilities. We got the probabilities. We just need to know the values of winning and losing. You go, what do you mean? How do you find values? Here's what you do. Go back to the cost. How much does it cost to play this game? $3. Okay? So this is how I always started. It costs you $3 to play. So if you lose the raffle for this outcome of losing, if you lose, how much did you lose? So put -3 because you lost $3. That comes out of your pocket. So in other words, money that comes out of your pocket is subtracted, right? So put that -3 for losing. Always in every gambling game, the money that comes out when you lose, that's the cost of the game. That's the price you pay for playing the game. You have to fork over $3. So when you lose, you lost 3. Does that make some sense? Now, we have to deduce the value amount associated with winning. What do you think that's going to be to win? Well, go back to the prize. What do you know about the prize, ladies and gentlemen? What's the value of a PlayStation? $600. You might say, oh, I want a PlayStation. I know, but the value of the PlayStation is $600. So let's pretend for a second you didn't even win the PlayStation. You just won a check for $600. Now pay attention to what I'm going to say. How much money did you win? How do you guys know it's $597? You're right, it is $597. How do you guys know that? Because 3 of those dollars were what? Were yours. Is that right? So you put in $3. So it is always what you net. In other words, you have to always subtract the difference from what you put down. So I know you're going to go around and tell your friends, guess what? I won $600. I know that. But what's the problem? You really netted what? $597 because 3 of those dollars were yours. So ladies and gentlemen, this is how you deduce the amount of winning and losing. Because to use the definition, we now got to take that $597, the x value, times 1 over 500. We now got to take that -3 times $499 out of what? 500. This times this, and this times this. Now, do you guys remember, and I'm going to put this here, do you guys remember from arithmetic, if you take a whole number times a fraction, right? This is -3 times $499 over what? 500. What really happens here? Do you guys know? If we do a little bit of arithmetic, how do you guys do that? Do you guys remember? You multiply how? $597 times 1 is $597. That's over 500. And then what is this? This is minus what? It's 3 times $499 over what? 500. And then what happens here? 597 minus 3 times 499. Remember, why do I get to put this over the same denominator? Do you guys remember? Because when you add or subtract fractions with the same denominator, what do you really do? You keep it all over the what? You keep it all over the denominator, and you add or subtract the numerators. But I'm going to have to put this in my calculator here. Okay, so this is going to be about how we use our calculator. Easy peasy lemon squeezy, how we use the calculator. You guys see what I'm saying? So this is the arithmetic we're going to do in our TI. And so I'm going to go to the TI. Let me scroll out here. Okay. Parentheses. What do we do? 597 minus 3 times 499. Close that. Divided by 500. And what happens now? Do you guys know? What do you think we just got? This is negative point what? 80. Mu is negative 1.8. Sorry, negative 1.8. So I use the definition here to compute the expected value or the mean. Now notice something here. This is negative, right? What does this mean? Well, remember, a negative means it comes out of your pocket. Is that true? Remember that? We assigned that value for losing money. So what this means is that you have what's called a negative expected value game. You have a negative expected value game. Not a positive, but a what? That means every player that plays this game loses $1.80. That's what it means. So when you play, remember what I said earlier? Gambling, generally speaking, is about you losing. And you look at me and you go, oh, no, that's horrible, Mr. Judge. I win and I have fun. And yeah, I know. But generally, more people lose than win. And at the end of the day, the long run average, when we can summarize this, and summaries are really great, everybody lost $1.80 who played. That's just a summary. That's the average. So in this raffle, players lost $1.80, and that casino or the people who did the raffle gets $1.80. So somebody loses, somebody wins. So if you lose $1.80, the people that did the raffle got $1.80. And they're happy because they got $1.80 for every ticket. But for the player, you lost $1.80 for every ticket. And that's what makes this world go round, ladies and gentlemen. It isn't about having fun. It's about making what? Money. It's profit per ticket. What? Hey, Gabriel. So let me give you a call, man. All right. What time is class over? 10:05. What's your next class? 10:25. Are you in the lab?
Yeah, but my class ends at 10:10.
Okay. All right. Okay, you guys okay with that? Everybody loses $1.80. This is a real purpose. This is what makes the world go round. You may not think it does, but it does. I'm going to share with you guys another example, but I want you guys to see the relationship between a raffle and that formula. This formula is how you do things. Expected value. So let's go back to Vegas again. You said, you know what, Mr. Judge, I love the slot machines. Maybe you say, I love the 25-cent slots. Every game in Vegas is a negative what? Expected value game. Every game. Every game in Vegas, all right? You lose 10 cents. Like, for example, This is an example. I don't know what the expected value is for a 25-cent slot machine, but I know one thing for certain. It's a negative expected value game. Because every game in Vegas is negative expected value. You might say, what are you talking about? Yes. So everybody who plays that 25-cent slot machine, if it's negative 10 cents, because that's 10 cents, what do you guys think is really happening? Everyone who's playing is really doing what? Here's your dime, here's your dime, here's your dime, here's your dime, because it's a negative expected value game. So instead of you looking at it like saying, oh, look, somebody just won, they're jumping up and down, and I'll say, yeah, they might have won $50. But a lot more people what? Lose. And at the end of the day, the average per game played is that everybody contributed or lost 10 cents. It's a long run average expectation. What do you guys think? That's what makes the world go round. So the next time you guys are in Vegas and you're gambling, what do you guys want to think about? Whatever game the person is playing, I know people win, more people lose, but at the end of the day, the long run average is that people are just simply, here's my money, here's my money, here's my money. And that's why the casinos are what? Well, they have bright lights. Somebody has to pay that light bill. They have subsidized food in the menu. Somebody has to do that too. You guys know what I mean? So that's the deal. That's what's going on. Every game is expected. It has a negative expected value game in Vegas. Because the purpose isn't to have fun. The purpose is what? Profit per ticket what? Sold. It's the end of the deal. Now, anybody have any life insurance? Good for you. Good for you. Why do you guys want life insurance? Yeah, I know. I know. It's nice to have life insurance. At least have enough to what? Bury yourself. All right, give yourself a nice burial. It's cheaper to be cremated. Anybody here want to be cremated? I'm going to be cremated. Anybody here want to be buried? Okay. Some people want to be buried. Some people want to be cremated. See the chat. Nobody there in the chat wants to be. Good morning. See Yapa. You got 5 people in the chat today. So, okay. What's cheaper? Cremation or, huh? There's what? Well, yeah, and it'll be expensive. Can you imagine? Gosh. Huh? And and then sometimes they don't even maintain it. I know. I got an email from family this weekend, angry that Rose Hills hasn't maintained my grandparents' and my mother's site. You imagine? You're gone. Yeah. Yes. Oh, you know about that, huh? Yeah. So it's my family. I didn't even comment to the group text. I was just like, oh, geez. So I'm going to be cremated. Where am I going to put my ashes? Dodger Stadium. On the infield. I'm going to tell my daughter, once you're running down in that infield, I want you to toss my ashes all over the place. Let's go crazy. Yeah. I guess you can't really do that. Maui, maybe? Can you get your ashes in Maui? Actually, I actually like the Kauai better, but what do you guys think? Can you do that? I've been told you can't even do that anymore. Cancun? Can I go out there in Cancun? Oh, did you? On the beach? In the ocean. He wanted to go to Cancun, huh? Did they let you do it? Really? Somebody told me you can't do it in Hawaii. So another other class yesterday said, because I gave them the expected value lecture too, and yeah, it's all it's always, I don't know. I mean, so yeah, yeah, yeah. There's always something, some weird thing. I don't know. Maybe go to Yosemite and drop my ashes out there. How's that? Go in the wilderness and it's even better. Anyway, here's a life insurance policy, ladies and gentlemen. I'm going to say to you guys, this is how life insurance works. There's a $25,000 life insurance policy that costs. Say, how much does this stuff cost? That costs about, let's say it's $1,200 per year for a 25-year-old male. Are there any 25-year-old males in the room? Good. Okay. If the probability of a 25-year-old male, right? 25-year-old male lives, probability of a 25-year-old male lives to see 26 years is 0.98. Compute the expected value. So this is how this works, ladies and gentlemen. We're going to use that formula. This is what I mean, how the world revolves around that formula. Life insurance, raffles, gambling. This is all about the average and the mean, the expected value. So you might say, okay, well, how in the world is this question just like gambling? Well, what are the outcomes for a 25-year-old male? Now, this is particularly, you have to be a male who's what? 25. And I'll explain to you why after we go through this, right? So what are the outcomes for that male? You can live, or you can what? Yeah, but let's actually say it this way. You can live, or you cannot live. So there is X probability. Here's what P of X. Okay, you guys okay with that? So let's go back and read. You guys agree if you're a 25-year-old male, because this is how life insurance works, right? You got to pay money for that policy. Those are the terms. You say, what are the terms? What does it cost? It costs what? $1,200 to do what? Do you guys know what they mean by that? What does that $1,200 represent? And what about the $2,500 or $25,000? I apologize, right? Well, here's the deal. If you live, remember we have to think about this. If you live, how much money do you get for living? Just for living, how much money do you get when you buy life insurance? You don't. You know what you do? You lose money. How much do you lose? $1,200. That's the cost of the policy. So you lose $1,200 Just for what? Living. What's the benefit, though? If you don't live, how much do you get? I should say. Well, I know what you're going to say. You're going to say, you know what, Mr. Judge? I get $25,000. No, you don't. Your beneficiaries get a check for $25,000, but $1,200 of it was yours. What does that mean? Where's our calculator? Come on, TI. I can't see you. Whatever. How much does your family net, ladies and gentlemen? You always have to give the net. Always, always, always. 25,000 minus what? 1,200. You guys okay with that? What do you get? Is that $23,800? Yes, it is. So really the net, and I'm going to have to say that again. I know they get a check for 25,000, but remember 1,200 was yours. It is always the what? The net. So your wife or your beneficiary, your kids, who knows, they get to have a party. You know what I mean? Maybe they take the ashes where they pay that fee in Mexico and they go to Cancun. How come I can't move that out of the way? What's going on? Oh, maybe I'm not. Whatever. This is the check they get. I know it's $2,500, but you netted $23,800. That's the outcomes here. Now, what's the probability of living, ladies and gentlemen? Because they gave you that information too. What do they say? Probability is what? It's 0.98. Is that true? 0.98. All right. Now, what's the probability you don't live? What's the complement of living? It's not living. What's 1 minus 0.98? Do you guys know what that is? 0.02. So what you now have is the x value and the p of x. You got the x value and the p of x. So I can find the x times p of x. Negative 1,200 times 0.98, and then 23,800 times 0.02. You're going to get your mu, ladies and gentlemen. What is mu? Mu is negative 1,200 times 0.98 plus 23,800 times 0.02. This is your expected value. So let's find this out. Let's see what this is. Let's go to the TI and it's really weird on my little thing here. I don't have it, but whatever. Odd. Okay. So remember, where's your negative sign? It's down here. Is that right? That's a negative sign. You got to put negative 1,200 times 0.98 plus 0.02 times, all right, let me do every detail, 23,800, okay, times that 0.02, just like I wrote it down, just so you guys don't freak out. What's the expected value? What is it? It's negative 700. Is that right? So what does this actually mean? First of all, again, it's negative. So what does it mean, ladies and gentlemen? It means everybody, well, I should take this back. Every 25-year-old male is really doing what to the insurance company? They're giving them $700. And that's why the insurance policy exists. Every 25-year-old male is giving insurance company $700. Because the mu value is negative, that means every person who buys the policy loses money. Not really. You say somebody died and they got 25,000. Well, they netted, you guys know the story. But more people what? More people lose than win, or let's rephrase that. More people live than not live. You say, what's the chance of living? About 98% chance. What's the chance of not living? 2% chance. So the point is, insurance is not really what you think. Life insurance. It really exists to make the insurance companies what? Money. That policy makes them $700 per person. This is what makes the world go round. Your car insurance. Anybody have car insurance? Guess what? That has a negative expected value. Okay? All insurance has a negative expected value. Because what's the purpose of it? To make the insurance companies money. It is not what you think. It's not so that you have a safety net. The real bottom line purpose is insurance companies will design any policy to have a negative expected value. Just like Las Vegas. Every game in Vegas is a negative expected value game. Every game in Vegas is a negative expected value game. So I know it kind of sounds horrible. You go, boy, Mr. Judge, that sounds horrible. It's not horrible. It's the way it is. It's how life insurance is. This is how even gambling is, You guys buy those insurance policies for products you get. You guys know what I mean? Is it worth it? It might be. But at the end of the day, what's that insurance really for? So that the people who sell it to you make money. That's what it is. Because it's going to be a negative expected value. It's not because they're generous. They go, hey, guess what? We have a nice policy for you just in case. No, they make money on the insurance too. Even though you might say, well, does that mean I don't buy insurance? No, I got news for you guys. The next laptop I buy is going to have insurance. Because I've already knocked this laptop out twice. And Apple says they rebuilt it. Really? I don't know. I'm not so certain they rebuilt it. But I knocked them out twice. So that's why I know, oh my God, you imagine? I'm going to have to get some life insurance for my laptop. Get some life insurance for your PlayStation 5. Your Xbox. Life insurance in case something goes out. What do you guys think of the expected value formula? Pretty nifty? Yeah, it's a pretty good formula. Anyway, let me give you a couple of other formulas. So if I go back and look at this, let's go back and look at the browser. All right, because I want you guys to recall this. There it is. Remember I said for every distribution, what do you have? You could compute the mean, variance, and standard deviation. Well, here's the formulas for variance and the formula for standard deviation. So the variance formula, represented by sigma squared here, is going to be this. It's in the notes, but let's work on that here. Okay, so where are we? Okay, TI, there we go. Here's my iPad. This is now x squared times px minus mu squared. This is the variance. Now, you might say, well, why do I care about that? Well, in order to get the standard deviation, because the standard deviation is the square root of the variance. In order to get that, we need to take that square root. I know you guys can't see. Let's make it so you can. Okay? So this is what I need to do. I'm going to get this value here. I'm going to color that green, I think. No, that's not what I want to do. Let's color it dark green. Let's get that standard deviation. So here's what I want you guys to see. So earlier today, let me get this out of the way. Let's go to Excel. So now let's make sure it's on all the same parameters. 20 in the center there. I'm going to put here now. X raised to the second power times that probability here. P of X. And maybe over here I should have put that times as well, just so it's clear. Asterisk means times. And here we go. So now it's green. So here's what we have to do. We're going to have to take the X value and raise it to the second power. There we go. And then I'm going to multiply times P of X here. Okay? That's what that means. And that makes sense because 0 squared is 0. And then times P of X is just, well, P of X is 0, sorry. But we can do autofill, and I'll do that here. Meaning do this for every value of X. Now, remember, what am I supposed to do here? I'm supposed to add these numbers here. So I'm going to focus on this formula here, okay? So what do we get for that sum? Do you guys see what we get for the sum? What do we get? What's that number there? Isn't it 5.504? All right, so maybe I'll do this now. Let me be careful here. Yeah, here's what I'm going to do. Here we go. All right, let's go to the iPad, if I can find it. I'm going to bring it in right in here. So I want you guys to see the details here. In green, I actually highlighted this in the wrong way. You see what I just found here? That's the green. What number is that? That's sum of X squared P of X. That is 5.504. Do you guys happen to know what mu is? Oh, what color did we use there? I guess it's orange in this picture. This is mu. That is the sum of X P of X. What number is that? Did you guys see the number? What number is that? That's mu. This is 1.866. Okay? Now that is mu. So what you'll get here now is this. This will be sigma squared will be what? 5.504 minus 1.866. And we're going to do what with that power? We're going to square that. That's going to be power 2. All right. What is this number going to give you? Oops. What does that give you? Sigma squared. But I want to emphasize this number here. This is in green in that chart, and this is in orange, because this is what you guys are going to need to do to compute the variance and then ultimately the standard deviation. So hopefully you guys can see those numbers there. Right? You guys see my point? Let's move it down here. That's what you guys do. Now we're going to use the TI and we're going to compute this variance. All right, TI. 5.504 minus 1.866. Square that, and what do you guys get? 2.022. If we go to the nearest thousands, okay? Going to the nearest thousands, this is what this is. So you can get the variance for any distribution. There's your variance here. Now, what's the real purpose of getting the variance? Because what you want is really the what? Standard deviation. Remember those two measures? this is how we get standard deviation. It's that sigma. So if you said, Mr. Judge, why do you have this other shape too there? See if I can get that in. See that? This is sigma, by the way. Let's move this out of the way. See what this is? This is sigma. What does it look like to you guys? It's like a sideways 6 or like an O with a fancy O, but it's a Greek letter. So the standard deviation represented by sigma, okay, this is SD for standard deviation. All we're going to do is say, okay, we're going to take that variance of 2.022. We're taking the square root of that. All, of course, in the TI. So second, there's a square root, 2.022, and you end up getting, what is this number going to be? 1.42. There's thousands. The 1 is in the thousands position. The digit to the right is a 9. What does that give you? 1.422. So, ladies and gentlemen, and I don't know what color to use here, but let's use blue. This is how you can also get the standard deviation for any distribution. You're using those two formulas here, or those two relationships, okay? What do you guys think about that? So I wanted to make sure today, because we're going to still work with some more, ideas about variance and standard deviation for our distributions, because you might say, hey, Mr. Judge, does the binomial distribution formula have a mean? Yes, it does. Does it have a standard deviation? Yes, it does. What about Poisson? Yes, it does. What about the normal distribution? You don't know about that yet? Yes, it does. They all have a mean and variance. Any distribution you deal with has a mean and a variance. So from first principles, by definitions, this is how you compute the mean, variance, standard deviation for every probability distribution you see in your life. This is just by definition. So in your homework, you might have said to me, boy, anybody know what I'm talking about? Let's go to the browser now. Okay, browser. Right? You go, okay, well, it's over here.